and Darboux transformations. Such transformations gives us a very, very nice a natural way to discretize such surfaces. In particular, the Bianchi commutativity theorems gives us how 4 solutions of the, say, the sine-Gordon equation, which describes surface of constant negative curvature, can be how 4 solutions are, say, connected through Becklin transformations in purely algebraic means. So the idea is to encode inside the equations also the transformation properties of such discrete surfaces. So the third dimension here is again of the same nature as the discrete equation, the discretization of this surface. So many people recently give a lot of attention on such discrete objects, which deserve to be studied as they on their own right. Okay. So, what are these objects like lattice equations? First of all, we have a lattice, which all you know that is generated by some linearly dependent vector, say on Rn, and this say linear combinations with coefficients on the integers. So many different vectors generate the same lattice, okay? But this determinant where Vienna, V1, Vn columns does not depend on these generators, okay? So say on Z square, we have this linear combination. And this is a discrete analog, say, of partial differential equations in 2 variables. All right, so I'm going to denote f with, say, complex valued function, which depends on 2 discrete variables, n1 and n2. And instead of having partial derivatives, we have now commuting shift maps, S and T, which shift the first or the second, say, independent variables. So a quad equation is nothing but a relation involving all these 4 values assigned on the edges of an elementary quadrilateral. We will suppose that the equation is an irreducible affine linear polynomial, which depends non-trivially on all variables. Okay, and on this space we have we can extend by this space, say the discrete Z space, where Fj, this Fj capital means all forward shifted value in any direction, okay, up to some order, fixed order k. So here we have Z2, say, Z bundle, lattice Z bundle. All right. Examples of such quad graph equations are given by a recent classification by Adler-Bobenko and Suris. See here a list of equations which are integrable in a sense, in a sense that I'm going to explain later on. So the top of this equation is Q4. Q4 represents the superposition principle of Khrushchev-Novikov PDE, okay, and P and Q here, which are the parameters, which I forgot to tell you that we can have some parameters, say, on the edges of the graph, playing the role of lattice spacing, say, in its direction. Okay, here P and Q are parameters on this Jacobi quartic, okay? So this is the Jacobi representation of this master, say, equation, lattice equation. There is a degeneration diagram that degenerating these parameters, we can go further down to other equations in this list. Probably the most known one is the last one, which is the superposition principle of KdV, potential KdV. In 3 dimensions, there is also a classification of integrable equations, again by the same people, Adler, Bobenko, Suris, and especially on equations of octahedron type. These are labeled here by x1, x2, x3, up to x5. They're called octahedron type because they do not involve 2 values, namely f and f1 to 3. Okay, so these naturally define an octahedron, okay, instead of a full cube. All right, there exists also, the first one is called AKP. A is to distinguish from B, KP, and CKP. And KP is for, this is the superposition principle of Becklin transformation for Kadomtsev, Pedvashvili, PD. This is a Svarzian this is called the Svarzian KP. This is the modified, the potential KP, this modified KP, and the last one I think is called by the inventors, namely Nijhoff and Capel at Toda something KP. All these equations are classified quite recently in 2012. However, they had appeared earlier in the literature, and they were found by other methods. What I was saying, yes. So there exist also equations which have full, on all vertices of the cube, namely BKP and CKP. And also there are some Svarzian analog of these equations. So how was this equations were, say, classified, which property was investigated and they were classified. So let's take the simpler situation where we have a quad equation. So we impose the same equation on every face of a cube, and we impose initial values, these ones with the black dots. Okay, so each face of this cube carries a copy of a quad equation, PQ, and say R the new the third dimension, the parameter associated with the third dimension of the lattice. So using the equation on each face, we can find from this initial configuration the values uniquely, the values on the green points. So from the quad equation in this front, 1, 2, 3, we have 3 values. From the equation, we can evaluate uniquely this value here. The same on the left, say, quadrilateral, and the same holds for the up quadrilateral. Then we have 3 different ways to calculate the value of this point red here. There is no reason why these 3 different ways should lead to the same value. However, for these equations, this is the case. So independently of the way of calculating the value on this red point, gives us the same result. This is quite, this property reminds us, say, some sort of Penlevé property where integrability, say, depends on the particular way the differential equation appears. Okay. Now, one can argue that we can have another initial configuration of initial values, say this one here, and we can again, using the equation on each face, we can calculate the values on these 2 red points by avoiding, in the first case, that white point here, and the second case, that white point here. So in the first case, we calculate first this point, this green point, then from this, that, and from the upper quad equation,
Anastasius, I don't hear you.
some additional structures inside from the very beginning. So this structure is nothing but, of course, as many people say, this braid type relation. So imagine we have some deformation of paths, okay? So we have assigned values on alpha, beta, gamma, delta, epsilon, zeta, say, path, and we deform this path to alpha, beta, gamma, dot, delta, dot, epsilon, zeta by the quad equations. So here, first with bj, which I write the quad equation on which acts on the j minus j plus 1 factor, say. So we calculate first k, and then we go from the deformed path with bj plus 1 to delta prime, and then finally to gamma prime. There is also another way of doing that. Instead, we go first on bj plus 1, and then in this way, we again take the values on this deformed path. Key properties for these quad equations is that this, if we see this as a map, these maps are commute and they satisfy this braid relation. Of course, this is known as the braid group BM. And if we further impose that B squared is yes, is the symmetric group.
Can I ask a question?
Yeah, yes.
Can you return to the previous slide? The definition of Bj. So, what is B1? In the map B1, Bx on which factors? In the map B1,
B1.
Bj, let us consider the case J equal to 1, B1. So, do you have factor 0? So B1, in B1, Bx on factors number 0, 1, and 2. But do you have factor number 0?
So I didn't hear very well, but if I heard well, is what is B this map? So we just so we have 1, say 2. We number the number of vertices on this. Okay, alpha 1, 2, 3, 4, 5, or whatever. So this would be here. It would be J minus 1, some J minus 1, J plus 1, and so on and so forth. So
Then J be equal to 1 or not? J, okay. Do you have J? Look at the case J equal to 1.
For J equal 1, what happens to the map?
Right. So what is is it well defined? The case J equal to 1. Bj has factors number 0, 1, and 2. Is the factor number 0 in the map?
Probably yes. Maybe so. J should be greater than say 3. 1, 2, 3.
Greater than 1. So you start from J equal to 2 probably.
Yes. Oh yes.
Okay.
All right. So another graphical representation of this is probably everybody knows is this shift twist maps, say, that exchange, say, the second with the third strands here of on this configuration. So the Young-Baxter relation, or the braid relation, is that these two different, say, ways of making this strands here, we should have the same lead to the same result. So it is red, yellow, blue, and green, which is also this. This is also represented by this. If we take this product, say 3 times, it is identity. anyway, this is just another way to visualize this brain group. So apart from this group structure, say, of the equation, which have they carry these equations with them, there are also some other group playing around, and this is nothing but transformations, local transformations that transform solutions of the discrete equations into other solutions of the same equation. These are called also Lie-point groups of transformations. So if we translate the usual theory to the discrete setting and allow the group, the transformation to act only on the dependent variable f and not on the independent variables, which are discrete actually. So the only continuous thing here is f. So it is very natural to seek such transformations. And we define the discrete prolongation of this group action on the lattice Z space, which is just, say, the shifting of the shiftings of the values f. Okay. So in the infinitesimal level, these transformations are generated, as we know, with these vector fields here, which are the infinitesimal generators of the group actions. And this Q here is nothing but the derivative of the transformation with respect to the infinitesimal parameter, group parameter epsilon, evaluated at epsilon equal 0. So it is known that there is a very well known this thing, that there is a one-to-one correspondence between connected groups of transformation. They're associated, say, infinitesimal generators. And by exponentiating this, if we know this infinitesimal generators, we can reconstruct, we can find actually the transformation.
May I ask something? May I ask a question?
Yes, yes, of course.
For partial differential equations, not every infinitesimal symmetry can be integrated to a real group of transformations, as you probably know, right? For partial differential equations, the jet space is. So do you have finite dimensional jet space or infinite dimensional jet space here?
Infinite dimension.
You consider jets of restricted order, right?
Yes, we fix the order, okay? So for second order equations, we go just to second order prolongations.
Yes.
Okay, yeah. So, yeah, for fixed order, no. And this is known. And why should we search for such these vector fields? Of course, it is known because at this level, the equations which determine this Q is linear instead of non-linear group. The non-linear equations which should be satisfied for phi. So we go infinitesimally close to, say, of course, this is how Lie invented his Lie groups and Lie algebras. Okay, this is the exact analog. Actually, he found this transformation, his theory, by his study on differential equations. Okay, so simple definition here is that the transformation G is a leap point symmetry of the lattice equation if it transforms many solutions to another solution of the same equation. Okay. So, for instance, for second order, like the lattice equations we are interested in, we go up to the second order prolongation of these vector fields, and we act on the equation that this should be zero. This is gives us a determining equation, which linear one, which can be solved in principle. To find that equation, we differentiate this determining equations conveniently, such that to have at least a simple differential equation, and to determine from this the symmetries of the equation. So if we do that, the result is a set of infinitesimal generators, and which form a Lie algebra, and the symmetry group can be found by the usual procedure of exponentiating a vector field. So, the lattice invariants. What are the lattice invariants? Lattice invariants are functions which are not affected by the action of the symmetry group. So, for connected again groups of transformation, a necessary and sufficient condition is that this when we act with the symmetries of the generators of the group on this function, they should be zero for all V. So this is a system of partial differential equations which can be solved, homogeneous ones, which can be solved by the method, say, of characteristics. And as we know, this system of differential equations, the existence of such solution is determined by Frobenius theorem. Instead of solving this differential equation, we can go to the dual formulation and find these invariants purely by solving linear systems of equations, not differential equation, linear system of equations. This is accomplished by this correspondence, namely the differential of a function I when we take the inner product with V, gives us this say this relation here. So, in other words, the differential di is a solution of this system of the partial differential if it this invariance condition in the language of forms interpreted in this to find such differential forms, and if we write this condition, we get this linear system of equations. Okay. Relaxing now the condition of absolute is variable, we get the notion of relative or semi-invariance, namely functions which are multiple of the invariants. So invariants are semi-invariants of index 0. So let's have a concrete example here of what I'm talking about. So let's take these two vector fields here. One can argue that they are linear dependent, these things. However, this alternate factor here changes the plus to minus for for even shifts. Okay, so these are not linear dependent. And we have the second order prolongation of these two vector fields. Now the linear system of for what I was talking about is this one. So a simple row reduction here gives us the solution of this homogeneous linear system. And the two independent, say, one forms we are seeking is of this form, which are naturally live on say, yes, these are just these ratios, okay? In a similar manner, we can find also relative invariants, say S1 and S2. So the idea is the lattice, 4 of them. So there should be these four invariants should be are not functionally dependent, because 3 of them only are functionally independent. So there is a functional relation between the invariants on the edges. So let's write it here like f x, y, u, and v equals 0. On the other hand, the equation itself can be written by definition of the symmetry as in terms of the invariants. Okay, so we have two equations here for the invariants. So we can solve this equation unique. It turns out to be solved uniquely, and we have a map. A map. So instead of having an equation involving these values, if we go on for the invariants, then this is a map. Okay. Right. Let us take the KdV equation, for instance. This equation has a three-dimensional group of symmetries, which is actually isomorphic with isometries of Minkowski plane. So the Poincare group, say. So the invariants, let us take the simplest one, namely the translations. Okay, so invariants on each edge of this quadrilateral are just the differences, f1 minus f. The same also for this. As I said, this is these are functionally dependent, and there is a constraint, say, that if we eliminate f from this, we get this functional relation. And on the other hand, the equation itself can be written in terms of the invariants. So we have two two equations for the invariants. So we solve this uniquely for, say, U and V, and we get this map, which is known as the Adler map. Now, the consistency property for fields on edges leads us directly to the Yang-Baxter relation. So if we extend this on a third dimension, okay, x1, x2, x3, and then we assign now the values on the edges of this, then with the map which we have found from the quad equation, we can go, say, first from by R12, which means that we use the map on the first and the second component. Okay, so this dot means that we go x3 remains as it is. Okay. Then with 1, 3 means that we use the map to go from this, yes, using the map on this quadrilateral here, okay, and finally with 2, 3, okay, and so we have found the values from x1, x2, x3 to the double prime here values. And we can also take the other way around, namely 2, 3, 1, 3, and 2, 1, 2. And by the property of the lattice equations satisfy, then we are sure that these two results are equal. So these maps are Yang-Baxter maps. So in its original form, the Yang-Baxter relation is not for maps. Actually, it was invented by on the inverse scattering, quantum inverse scattering, and statistical physics by Yang and Baxter independently. And Drinfeld in 1992 suggested, instead of having vector spaces, to have just sets, and suggested to study such this situation here. Actually, such examples of solution were already known by Sklianin. However, this turns out to be a very interesting connection with integrable systems. So let's space here. So the invariants in this are just the diagonals on this setting. So the map here can be considered in this way here. And if we use the symmetry and the compatibility of the KdV in a dimension greater up, then we get a different Yang-Baxter map. And using the compatibility of KdV, even in a greater dimensional space, namely on a hypercube. Now KdV here is imposed on each face of this hypercube here, and we use the full group of symmetry transformation of KdV, and assign in this way the invariance of the full group, I insist here. Then we take other Yang-Baxter maps, such as this one here, which was known to the people working in general relativity, that this is the superposition principle of Harrison-Becklund transformation for the Ernst equation. So there is a very interesting connection here with groups of transformation and lattice equations and their compatibility properties of the lattice equations in higher dimensions. So it would be interesting to investigate also this connection to other equations defined on Z cube. So let's find out such an equation. Again, a very clever way to go to three-dimensional ways is again to use a KdV imposed on a cube, and to add all these equations together of KdVs, and then we get, if we do that, then alpha, the parameters disappear, and F disappears since this is symmetric here. So we get the discrete potential Kp equation. So we can ask again, what is the symmetry group of this equation? And this turned out to be isomorphic to complex affine transformations of the complex line. All right. Now the invariants naturally live on faces, and we are if we solve 1, 2, 3 equations in terms of u, v, w, then we get another map.
Just a question.
Yes.
Do I understand correctly that if you have an equation written on the cube that depends on two parameters, if the equation is such that you can rescale off the parameters, are they going to cancel for sure when you move to the map? So do the parameters cancel out because in the original equation you can scale them off?
The parameters of which parameters?
Okay, you have your discrete potential KdV on the cube, and there are some parameters.
Yes.
These parameters, when you use the symmetries and you move to the map, the tetrahedron map, they cancel out. Because your map does not depend on parameters at all. So is this because the parameters in the discrete potential KdV appear in such a way that you can rescale them with the change of the f's?
No, the parameters can exist, but they could also not are not present. So I know examples where we have KPs with parameters and KPs without parameters. Is this the question? The question is about which parameter? The parameters of the equation of the.
I'm talking about the alphas, alpha 1, alpha 2, alpha 3.
This is a coincidence. This is just this
Okay.
happens.
So the question is, if you have an equation and the parameters appear as here additively,
Yes.
that means that you can rescale the f's and rescale them off. Is it true that they are going to cancel out when you move the map by the symmetries?
I haven't understand quite well the question.
On the F, if you receive F, you can do one parameter, not three.
Yes, okay, that's true. Okay, so probably my question doesn't quite make sense. So don't worry, I'll think about it and maybe I will reform my question in a better language.
Mm-hmm.
So sorry about the interruption.
Anyway, so what now is this map that we get out from this situation here? And let's do it for this equation, as I told, this KP, discrete potential KP, has a very nice equivalent symmetric form, namely this one. So let's take the abelian group generated by V1 and V2. I remind you, V1 and V2 are these two translation, say normal translation and alternate translations here. All right. So here are the invariants, some invariants. They are related by these two relations, and on the other hand, can be written in this way, discrete potential KP. The Bow system has a unique solution. So even if we have 1, 2, 3, 4, say, equations, actually these are compatible, so it gives us a unique solution, which is this map. This map, as I say, explain a little bit in a short time, satisfies tetrahedron equation. And the first who studied such a situation were namely functional solution, set theoretic solution of the tetrahedron or Zamolodchikov equation is Igor Korepanov in 1994. And later on, there were some classification results on these tetrahedron maps by Korepanov, by Sergei Korepanov and his collaborators. Okay, Kasaev, Sergeyev. So let us take other symmetry group, a subgroup, namely the scalings and the alternate scalings, which are now the ratios. Again, this happens again, the same situation, and we get another functional tetrahedron map. And again, using the properties of the KP equations, namely posing that equation in a hypercube and using again the compatible nature of the symmetries, we can exploit, we can use the full symmetry of lattice potential Kp to have another different functional tetrahedron map. So that one that was observed for the KdV equation also is preserved for equations in imposing equation, three-dimensional equation on a higher dimensional, say, lattice. So on this, I'm going to explain a little bit further about this, the tetrahedron equation or Zamolodchikov equation. So a very nice geometric interpretation of this equation is given by this picture here, where we have four planes, which in a general, say, position, they meet along the lines. Similarly, three planes meet on four vertices, etc. So let us denote the vertex E with a hat, that one which does not contain 1. So this is just 1, okay, here. And similarly, 2, 3, 4, okay? And there is a, say, an orientation. So here, all leave from the same point. So this has no arrow. This has one arrow, two arrows, three arrows. Okay. So geometric representation. Yes. And then we move the one plane on the other across the point of intersection of the other point. So we have a configuration like this, but we have a new rearrangement, okay, of lines and so on and so forth. Now we have a different orientation, okay. Here we have zero vector. Here we have one arrow, two arrows, three arrows. So the two ways of should lead to the same result, say, for some object R. Okay, and if we name 1, 2, just 1, 1, 3, 2, we have this tetrahedron equation. Yes, there are also some other tetrahedron equation here. Namely, we know 8, I think, yes, 8 tetrahedron equations. So Korepanov suggested to start, was the first who addressed the problem of functional tetrahedron relation, and a picture which gives this correspondence, is like this. So we have a map that acts on the six tuple, say, of a set with coordinates x1, x2, x3, x4, up to x6, say. So we deform these cubes here by R1, 2, 3 in the first. So x1 goes opposite to the opposite on this cube here. So we got x1, 2, x2 opposite to this cube here. So we have x2 prime, and similar for x3. And we go in this way by the maps on the first, fourth, and fifth now components of the map, and like this. And there is also, and here we go on the opposite order of the map. So if we say we have these two ways should lead to the same result here for the prime of the dotted values. The equation of the tetrahedron itself have some symmetries, namely if we have bijection say phi and R satisfies the function of the tetrahedron equation, so the same is true for this, but these are rather trivial Gates equivalent transformations. A non-trivial situation is this, that if we take the twist permutation map on the first and the third indices, we make this composition of maps, then the resulting map is also a solution of the functional tetrahedron equation. The proof here is a rather curious composition of say R13 with the last map on 3, 5, 6, and we go from the one to the other by these successive transposition maps, permutation maps. Also, there is also some other symmetry, say, if we have an evolutive symmetry, okay, so sigma sigma squared is identity in evolution. So the map which is composed by this, say, in this way, is a new solution of the functional tetrahedron equation. So the same also is true if we change sigma 1, sigma 2, and sigma 1, 3. But this is a little bit trivial. So probably.
May I ask something?
Yes. Yes.
In lemma 2, the first line of lemma 2, let be sigma be an evolutive symmetry of the functional tetrahedron equation. You probably mean a symmetry of the map, not of the equation.
Yes, symmetry of the map. Oh, yes, probably. Yes. Thank you.
Of the map R.
If it was my mistake, yes, symmetry of the map. Yes.
Yes.
Thank you. Of course, yes. Symmetry of the map, yes. So, let us take such a symmetry of the map now. So we have the defining equation of the map. Okay. So if we take the conjugations, complex conjugations here, we see that okay, this is a symmetry of the map, of course. So that the holomorphic here on evolution is a symmetry of the bow map. If we take by the previous observation this composition and act on x, y, z, we end up with this map. Okay, but now this map has changed and involves complex now. So we have to decompose here on real and imaginary part, say. So the question is, what is this? Do we know any equation, integrable equation like KPs, which is associated with such a functional tetrahedron map? So now I'm addressing the problem of using this this solution of the functional tetrahedron equation to produce new examples of integral behind and write a vector analog of KdV equation. So this was introduced by Schiff in 2001 under the name Collapso equation. So this Collapso equation is again 3D consistent or compatible, and this is evident if we find, if you remember in the beginning of the talk, the F123 on the hypercube, say, from the initial data F1 and F2 and 3. So this is an invariant under any permutation of the indices. So this is compatible. It is interesting to note that from this compatibility, one can have in analogy with the KdV equation gave us to Kp. Now Collapso gives us a vector analog of Kp's, which is written here. So if I take a scalar case, the scalar vector, the real case, so this equation is just Kp squared. All right. The interesting is that if I take the complex scalar case, this Collapso gives us a correspondence, namely two equations. The first one is this, and the second one is this one. So it is a complexification of Kp. And this complexified Kp gives us this map here. One can go a step further up and consider the quaternionic case. So a vector here on V4 can be represented in this way with matrices. This is very well-known stuff. So it can have some, yes, and use the symmetry, the abelian group of transformations, subgroup of transformation. And so here, these are, in terms of the matrices, here is written the functional relations of these invariants are given in this matrix form, while the equation itself is given in this matrix form. And we can, well, we can find some solutions. I have found, say, we have found some solution of this equation. Which are presented here. However, in the generic case, only the first satisfy the functional tetrahedron map, while these two does not on their own. Maybe if we couple them together as entwining, say, functional tetrahedron map, maybe this I haven't checked thoroughly though. However, in the three-dimensional case, all these situations collapse into one solution, which is just the first case, since we have skew Hermitian matrices in this case. So I'm going to end this talk with some work in progress, where we have we want to explore more general symmetries, like potential symmetries, and this gives us, say, coupled Kp's equation. So the question is how symmetries and lattice equations can be, how this link can be explored in the case where we don't have enough symmetry, or in the case we don't have at all symmetry. So this situation can be seen in a concrete example. So we take the discrete modified. So it is X4 in the Adler-Bobenko-Suris classification, and Nijhoff in the Nijhoff-Capel it is modified KP. So clearly this equation is not invariant under any translational symmetry because of these guys here. Okay. However, there are some differences here which are obvious. So if we insist in writing this equation in this form, in the invariance of the translation symmetry, then we are forced to take also this invariance, semi-invariance actually, into account. So,
may I ask a question?
yes.
What are semi-invariants of a group? What do you mean by this?
Yes, these are not annihilated by the vector field. So when we act with the vector fields, it's not zero. It is a multiple of the invariant.
Okay.
So it is an index as a.
And if you act by an element of the group, what happens with this semi-invariant?
Sorry. Can you?
If you you said on the infinitesimal level, but on the level of the group, if you act by an element of the group, what happens with this semi-invariant? It is not invariant, but what happens with it when you act by the group?
It is a multiple of the invariant.
It is R. So by definition, a semi-invariant is a multiple of some invariant.
No.
Yes, probably it was my mistake that I didn't point it out very well. So
Would it call the projective invariant? The projective invariant.
So an invariant, an absolute invariant annihilates is annihilated by all vector fields here. So it is zero. So it is a multiple of the invariant. So we have a semi-invariant, or say, of index beta. Okay.
Yeah.
All right.
George Kokovikas wrote a comment explaining what happens. Thank you.
All right. So, all right. So these are invariants are related by some functional relations here, and that's it. But so we have 1, 2, 3, 4, 5 equations. So we don't have 6 equations to get, say, a function of the tetrahedron, a map. So let us augment. So we put by hand, well, actually not by hand, but this is a compatible, say, choice.
So do you impose this equation in order to obtain a Tetrahedron map then?
Yes, exactly.
So because we also have with Kulukas several correspondences and some symmetric relationships like that would give us an actual, well, Yang-Baxter map, but I guess it's the same.
Yes. Okay. So doing that, we get a unique solution, which is given by this vector, say, generalization of the KP functional tetrahedron map in terms of multisymmetric polynomials of two sets of 3 variables. Now, the interesting with this is that if we introduce inhomogeneous variables pi and qj, and we take this, this map is reduced to this map of KP. And actually, that equation that was added here, it is the KP equation. So what we have done here is that we have coupled modified KP with the potential KP in a consistent way, such that the new system is three-dimensional compatible. So one can think here that he introduces a new potential, and in terms of this new potential, the translational symmetry is admitted. So so one can speak for a hidden, say, potential symmetry of the starting lattice equation. Actually, this situation here also is valid for quad graph equations. And in recent work with Pavlos Kasotakis, Mace Netporski, and Vasilis Papageorgiou, we have seen that from quad graph equations, they can couple together in a consistent way, even different ones, not the same, exactly as the same as in this three-dimensional situation. So my concluding remarks here would be that the compatibility condition is in very good, say, goes together with the symmetries, which are by definition compatible with the equations. So it gives there is a lot of tools that can take from invariant theory and use these tools to produce, using this correspondence with functional tetrahedron maps and lattice equations, and to produce new integrable equations, or even study the solutions of the equations themselves. So thank you for your attention.
Thank you very much.
Thank you, Anastasios. Are there any questions?
Ask a question. So the methods you are using to go via symmetries from 3D lattice systems to solutions of the tetrahedron equation, can you take not only one system, but maybe a couple or three, and using the symmetries go to the solutions of the entwining tetrahedron equation?
Entwining.
Yeah.
So,
only entwining solution of the tetrahedron equation that I've seen is in Pavlos' paper in 2019, a very simple one. So I was wondering if somehow you can get maps, solutions to the entwining tetrahedron equation using symmetries of several 3D consistent systems. No, not 3D consistent, but the 3D lattice ones.
yes.
Yes, but this is for discrete symmetries, these involutive symmetries, and not the Lie point symmetries. Well, indeed, Sotiris, I haven't seen with using, let's say, this approach to get tetrahedron, entwining tetrahedron. If you have this symmetry notion that Tassos said at the beginning of his talk, that is, let's say, due to Veselov, then you can have, I think, yeah, you can have entwining. But, yeah. But I don't know, maybe Tassos can comment about that.
Well, actually, for entwining relations, I haven't studied very well, thoroughly. But I have seen some equations which are not consistent with themselves, but we need also other equations to be copied. So this can happen here. I don't know if I satisfy the question. If I answered your question.
May I ask a question? Hello?
There is something like a delay.
May I ask a question? Hello? Do you hear me?
I can hear you, but there is a little bit noise.
Is it better now? So, these discrete equations, the structures, they possess not only point symmetries, but they possess infinite number of continuous symmetries and the algebra of symmetries. I wonder how this algebra of symmetries can be extended to your maps. What happens if you differentiate these equations with your maps with respect to these symmetries? Is it possible to define, the symmetries of your map? Is this map a kind of continuous symmetry? The hierarchy. What happens with the hierarchy of symmetries of different equations when you go to these maps?
These are local. These are local 3 points.
No, I'm talking about higher symmetries. What happens with higher symmetries? The equations have higher symmetries you start with. You start with like potential, discrete, etc. You have infinite symmetries, not only discrete symmetries.
We are talking about if there exist higher symmetries.
I say that the equation you start with, potential to be discrete or whatever equation you listed here, they have infinite hierarchy of higher symmetries, not point symmetries.
Yes, there exist higher symmetries for
Right.
such equations. Yes.
Yes. Any kind of implication for the symmetries of your map is your maps also have some kind of inequalities, high symmetries or something. We have vector fields, which and your equations are in the corner of these vector fields, on the solutions. Can you, what happens with these higher symmetries when you move to your maps? Do you think whether this map remember these higher symmetries? Should be some kind of realization of these higher symmetries for the maps.
So, I have not understand. I have not heard very well the question. Higher symmetries exist for quad equations.
Yes. Infinite domain.
Of course, there exist and depends on 5 or 3 point. It depends on the direction of the lattice. Also, there are also extensions on the parameters, but let's forget about that thing. So, for say for the simplest one, there exist generalized symmetries, okay? And they go using recursion relations. Again, this thing works also for lattice or master symmetry. So you can expand your symmetry to 5 holding more points of the lattice. So this is the hierarchy actually, and this the hierarchy of actually these are. The interesting thing is that if you allow also the parameters to change, okay, then you have symmetries also on the parameters, and this gives you a flow. It gives you a flow for the differential difference equations here.
Yes, that's exactly what I mean. But do you have any implication for your maps? Do your maps have any kind of hierarchy built in?
Okay. If this okay, now I understand. If this has something to of the discrete equation. Yes.
Can you extend these symmetries to your maps in a sense of these hierarchies?
The equations by themselves they capture the whole hierarchy of the PDEs that come from. So this KDB here captures the whole hierarchy, say, of symmetry of the equation. So, in a sense, this is the main say very interesting thing of studying these discrete equations on their own. They capture also this the whole hierarchy of KDB.
Yes, but when you go to your maps, you forget about all these symmetries. My question, where are these symmetries?
Where are these symmetries?
In the maps. In the maps, you find maps. Anything?
In the maps. Okay, where are these symmetries in the maps? I don't know. This is a very interesting question.
I don't think there is work on this thing. I mean, no one has a map using higher symmetries even for lattice potential KDV and try to write the map using the invariants of higher symmetries, even the lattice potential KDV. I haven't seen it, but maybe someone knows. But I haven't seen it.
That was my second question. You just answered me a second. But my first question is that even with your maps you find, it should be some, some trace of the symmetries of the hierarchy. It should be seen in your, so your kind of map should have extra properties, hidden properties, which comes from the hierarchy of symmetries for the quadrilateral equation you start with.
Okay.
Yes, it can be.
I don't know. But, well, actually, this is a very interesting question. How these symmetries has to do with the maps? Well, if the question is known to you, I would like to hear.
The question is no, the answer is not.
Yeah, the question is?
The question is known to me, but the answer is not.
It's not. The answer is not. There is.
The answer is not known.
I cannot hear. I'm sorry. Anyway,
We don't know the answer yet.
at least me, I don't know.
No, I think he said that the answer is not known, but I'm not sure.
Ah, it's not known. Ah, okay.
There's this massive noise I didn't hear quite well as well. I think that's what he said.
Yes, yes, this is true.
Okay. Are there other questions?
Maybe one still one question, one small question. Can you hear me?
Yeah, yes, I can hear you clearly.
Okay, so at least one of your tetrahedron solutions can be produced from pentagon solution. From a pentagon solution, you see, there is such thing as a pentagon equation in its different variants, set theoretic and quantum. Okay, and that's enough. Set theoretic, for instance, we can take groups or just copies of one and the same group for those sets, because the group is a set, of course, and there is a very, very basic solution to pentagon equation, which says you that two group elements, call them A and B, A comma B, is transformed into A multiplied by B, comma B again. So this is very well known to all people, pentagon solution. And do you know that at least one of solutions that you have presented here in your talk,
yes,
can be produced in a quite regular way from that pentagon solution? And also, I would like to develop a bit more this question. There is that regular, more or less regular way was invented by Kashaev and Sergeyev, and I am sending the reference here on our chat where to find their work, and it goes like this: first you have pentagon, then you have a 4 simplex. You see, 4 simplex is even more high dimensional than tetrahedron. Tetrahedron is a 3 simplex, and 4 simplex is the pentahoron. You see? Yeah. And then you can produce from that. Okay, you go from pentagon to pentahoron, and then you can take some analog of what is called partial trace in the theory of quantum equations, like quantum Young-Baxter. You take an analog of that partial trace, and then you obtain one of your solutions presented here. So do you know this fact that this comes from pentagon? And even more important, did any people study this thing that is producing tetrahedron, functional tetrahedron solutions from pentagon? Because I said this goes in a quite regular way, but that pentagon solution that can produce tetrahedron solution must also, there must be 2 pentagon solutions, and they together must satisfy what Kashaev and Sergeyev called 10-term relation.
10-term, yes.
10-term relation, and in some cases, that 10-term relation is not so, does not happen so rarely, so seldom. It happens sometimes that it does hold. So what I wanted to ask, is there anybody who works in this direction? Thank you.
Well, actually, I'm not an expert on this statistical, say, functional pentagon, or I just came on this subject here on my study of symmetries with say equation of this form, and turn out to be a very interesting connection here. I would like to see all these relations with pentagon and ten-term and higher simplex equation, Brucha decompositions. I just have seen, say, occasionally the names of all these equations. So.
Okay, I will write to you personally about
yes,
that.
Yes. Thank you very much.
But what I want to say is that there is, of course, some mysterious symmetry or something like that, something very mysterious, because that 10-term relation sometimes hold and sometimes does not hold, or maybe as it is supposed to hold for 2 pentagons. So maybe just we don't know the right way to find the other pentagon for a given pentagon. So, okay, thank you. I will write to you about this.
Thank you.
Thank you very much. So, I suppose there is no other questions. Anastasia, thank you very much. It was very interesting, and I hope to return to the subject of your talk at our working group. Satiris knows about it, so it could be we continue it in some private communication. I hope
that would be very interesting.
Actually, Pavlos once gave a talk on your other paper in this group, and we had a nice discussion. So I will tell you more about it later.
Okay.
So there is also a technical person. A couple of people asked if you could make available your slides.
Oh, these slides here?
Yes, on your screen.
No, yes, I would really love to have a copy of your slides, because sometimes you spoke too fast for me to follow, and would like to take a look more carefully.
Of course. How am I supposed to do that?
If you send it to me,
I don't know. Probably you can send it to the organizers, and then organizers will distribute it on demand.
All right. Thank you.
If you do this, that will be okay.
I'll do that. Yes, of course.
No, thank you. Thank you very much.
Thank you, all participants. We finished. Good evening.
Έλα, yeah.
Good evening.
Bye.